Hi, my name is Ju-Chan Kim, and I made this Google Collaboratory notebook for molecular dynamics simulation. If you have used my code in your research, please consider citing my work. Please read those instructions before running your project. As written here, with this notebook, you can perform all-atom MD simulations of general biological systems with free of charge Google Cloud computing resources. Before running any cell, please check your runtime is set to use GPUs. For free sessions, select T for GPUs. Below, you can see folded sections. You can click Open each section to run its component cells. At the beginning, set the name of the working directory that will be generated inside your Google Drive. I will name it BRD for bromodomain. Clicking the left-hand play button will automatically start the runtime and run the code written on that cell. Please authorize this notebook's access to your Google Drive to back up your progress and manage large trajectory files. Don't worry, this notebook will create a working directory and do everything inside. Wait for a few seconds. When there is a green check mark next to the cell, it means the code execution has finished. Now you can pick a package among these 3 cells and install it. If you are not planning to use machine-learned or semi-empirical quantum mechanical force fields, install minimal package to save your time and resources. However, you should install the analysis package afterwards. It took little longer than expected, but as the resulting lines say, you can see that a new directory named BRD has been created inside our Google Drive. So I can proceed to the step 1-1. In this tutorial, I will simulate a protein-ligand complex of a BET protein and a bromodomain targeting ligand with a PDB ID of 6K04. I will write down its PDB code in the blank. And on RCSB website, we can see that the official residue name for this ligand is called CQF. I will write down CQF in a place for non-standard residues. When I run this cell, it will look for any intrachain missing atoms and try to fill them in. Now it's time to add hydrogen atoms. This is extremely important yet overlooked step, since adding the hydrogens with correct names and correct places is sometimes a very tricky job. Among many tools, the tool I most recommend is Reduce, since it is less buggy and works quite well with protein-ligand systems. However, it can only consider protonation states for physiological pH. So if you want to produce a protonation state for a different pH, please choose other tools. Luckily, the result got out well, and you can focus around the ligand to check the bond and atoms are correctly attached. Please make sure that your system has correct atoms and bonds, since most errors and subsequent steps will arise from this. Now when you go and check your Google Drive, you can see that the starting structure.pdb file has been created as well as some other files. Now let's start the step 2. We can choose amber or charm force fields for biomacromolecules and several models for waters and ions. There are special force fields for molecules or residues that are not recognized by those macromolecular force fields. Anyway, let's run for amber 14 force field. The cell immediately says that the ligand CQF is not recognizable by the amber 14 force fields. Among auxiliary small molecule force fields, I will choose SAGE, which is more accurate than GFF and does not require additional package installations. You run cell 2-2 and get nothing since you don't have any non-canonical amino acids in your system. In cell 2-3, you should choose the parameters for your simulation. First, you select the ionic strength of the solution environment. And the thickness of the water blanket around your system. For faster simulation, you can set rigidify water molecules and set constraints, and increase hydrogen's virtual mass to increase the integration time step size. I will set the H-bonds constraint and set the hydrogen mass to 2.5 atomic mass units. You set the mix precision for the balance between the cost and accuracy. With the constraint set above, we can try increasing the step size to 3 femtoseconds. Finally, set the system's temperature in degrees Celsius. When we run this cell, we can see that the solvents are added to the system and the simulation object is created successfully. Then the code automatically energy minimizes the system prior to the simulation to remove any bumps. When it's finished, we can see this beautiful cubic periodic boundary condition box of our system. Now let's run the simulation. We will first raise the system's temperature to the desired 25 degrees Celsius in a microcanonical or NVT ensemble. The equilibration time will be 50 picoseconds, and we will backup process every 5 real-time minutes. And let's set the positional harmonic restraint on heavy atoms for less fluctuation. It is blazingly fast since the system is small. When it's finished, we can check the equilibrated system snapshot by running this cell. No elongated or crazy bonds. Nice. And we verify the temperature convergence. We check whether the system's apparent temperature stabilizes around 25 degrees Celsius. Yes, so we proceed to isobaric or NPT equilibrium. We set the same equilibration time, 1 bar for the pressure, and half the strength of the positional restraint. We can see that due to the added barostat, the simulation is a little bit slower this time. We check the temperature and density converges to a certain value, and also check for the integrity of the system by looking at the snapshot. Looks fine so far, so good. Now we can make the production run. Let's run for 10 nanoseconds and save the snapshots to the trajectory every 5 picoseconds. And it started. It takes about little less than an hour, so let's take a break and come back later. Welcome back. I did not pay much attention to while running, so Google automatically quit my job. So let's restart the session. Connect to the GPU runtime. If we enter the same working directory name, this notebook will recall from the last saved progress. Since we have finished the simulation and are now interested in only analysis, I will install the analysis package. When we check the contents of the Google Drive Working Directory BRD, we can see that trajectory XTC files containing the position data of atoms in the simulation objects saved in smaller fractions. The package installation is complete, and the cell says we have been performing the production run. So let's head to cell 3-3. Meanwhile, we can fold back the finished cells to scroll down less distances. So we are now at the cell 3-3, and we see the simulation had been finished without errors for 10 nanoseconds. So let's decide to end the simulation here and proceed to the analysis step. You may extend your runs by running the cell 3-3 desired times. Now we are at the step 4. In the cell 4-1, we will concatenate the fractions of trajectories into one and bring back any molecules that escape the periodic box. Then it will center your molecule and minimize the translational and rotational motions for the better visualization. By checking the box, we can additionally smooth the trajectory, removing the high-frequency motion noises. It takes some time for trajectories with long simulation time or frequent samplings, so please wait. When the processing is complete, the cell will try to show you the resulting trajectory as an animation clip in NGL widget. But it is slow. So for large trajectories, I recommend you to download your final trajectory and view with external molecular viewers like PyMol. As you can see, you can choose which trajectory to visualize among NVT, NPT, and the production run. Trajectory looks fine, so let's proceed to other analyses. In the cell 4-2, you can cluster similar structures in different frames in your trajectory and extract representative structures of each cluster. Set the RMSD cutoff value for the clustering and run the cell. Again, for large trajectories, this will take time. I skipped some time here. And we can see that even with the RMSD cutoff of 0.15 nanometers, we got only single cluster, probably because our system was very small and the structure did not change a lot. The centroid structures of each clusters are saved at the different frames of cluster.pdb file in your working directory. In the next cell, we can calculate the root mean squared deviation of our system. At first, it shows the whole structure's backbone RMSD change along the course of trajectory. When you change the option, you can also view the RMSD changes of protein and ligand separately. In the next cell, you can calculate the change of radius of gyration, or ROG. It gives a good measure to the size of a globular protein. It looks like it hasn't changed a bit, but you can click the auto-scale button to zoom in and see the small fluctuations in the size change. A steady ROG value indicates the rigidity of a protein-folded structure. In the next cell, you can calculate the relative free energy surface of the system along the two variables, RMSD and ROG. A system's free energy is calculated from the kernel density or probability distribution of that macro state. We got a nice 3D landscape plot of our free energy, and because the system's radius of the gyration hasn't changed much during the course of the trajectory, our system did not have enough chance to get sample from broader values of ROG. So we got this relatively flat surface along the ROG axis. In the next cell, you can calculate the heavy atom root mean squared fluctuation or RMSF value of residues. You can think of it as a measure that shows the flexibility of that residue. In the next cell, we can draw a Ramachandran plot of our protein along the trajectory. A Ramachandran plot shows the phi and psi angles distribution of given protein, summarizing the secondary structure elements. Data from the different time points will be shown in different colors, so you can get track of the structural change along the time course of our simulation. In the next cell, we can run surface area analysis. A residue's surface area can be defined in various ways, but we are going to use the definition of solvent-accessible surface area, or SASA. When we type the index of the residue we want to investigate and weight, it will give ESAS a change over the course of the trajectory. However, the Schrake-Ruppli method of MD-Traj used in this step is a bit slow, so please wait for a while. In the next cell, we can count the number of hydrogen bonds formed between two given residues. I typed 13 and 103 for the 13th residue aspartate and 103rd residue arginine. It shows that a single hydrogen bond is seldomly formed between the aspartate and arginine during the simulation. By leaving the second index number blank, we can count the number of hydrogen bonds between the first residue, aspartate 13, and the solvent water molecules. In the next cell, we can perform the secondary structure analysis using DSSP algorithm. Here, you can see residues that change its secondary structure from helix to coil and back to helix during the course of trajectory. In the next cell, you can draw a DCCM, which stands for Dynamic Cross-Correlation Matrix. It is a heat map showing the pairwise residues' motion correlation throughout the trajectory. The bluer pixels indicate the strongly correlated residues. In the next cell, you can perform the principal component analysis, which is a powerful technique to extract the key features in collective motions of atoms. You can show major principal component in each axis. And from the color of data points, you can get a grip of trajectory's course over this phase space. You can also do three-dimensional PCA too. To visualize the motion that each principal component represents, you can run this cell. The cell animates the principal component to a periodic vibrational motion. We have finally finished the step 4. Let's start the intermolecular interaction analysis. In the cell 5-1, you can visualize the intermolecular interaction with the software PLIP. In PLIP, 8 different types of interactions can be defined and shown in different colors. You can choose a ligand to get a 3-dimensional interaction diagram in the menu. The NGL widget takes a while to get reloaded, so please be patient. In the reloaded widget, we can see the interaction between the ligand CQF and the BET protein. Interactions are shown in lines in different colors. We can see the red hydrogen bonds and gray hydrophobic interactions. In the next cell, we can actually get the quantitative estimate of a binding energy. From the previous widget, we can check the chain ID of the ligand CQF is B. So we type B in the ligand chain box. We can leave the receptor chain box empty to calculate the binding of CQF to the rest of the system. Now we can finally run MMGBSA. In MMGBSA, you must choose the GB model and the values for solvent and solute dielectric constants. I will choose GBN2 and dielectric constants of 78 and 7. You may vary the value of the solute dielectric constant from 1 to 20. This code for MMGBSA is written by myself, so the result may differ from the MMPBSA or MMGBSA code from Amber Tools. Since my code is not extensively tested against the benchmark datasets with experimentally determined binding energy values, please use the resultant values with caution. Now you can see the energy component values variation along the simulation time, and the nice bar graph of each interaction energy components. But what we have here is the binding enthalpy, so we must determine the entropic contribution to estimate the binding free energy and binding constant. We use the interaction entropy and C2 entropy approximation method to estimate the binding entropy from the single trajectory. To get the standard error, we employ the bootstrap sampling. Here I choose the bootstrap sample size of 10 to the power of 5, which is 100,000, but you can change this value. We got similar values of binding equilibration constants, which is about 11 nanomolar. This value we got is pretty close to the experimentally determined Ki value of 9 nanomolar, which is pretty intriguing. You may calculate the binding entropies using quasi-harmonic approximation, but since it is very time-consuming, I won't demonstrate it in this collab-free session. Finally, you can check the sources of Python packages I use while writing this code. Okay, this is it. Was this video tutorial helpful? If yes, please hit the like button, and I will think about creating another video for the simulation of proteins with non-canonical amino acids. If you find this MD in Colab tool helpful, don't hesitate to share it with other colleagues and improve scientific community. Thank you very much.